Okay, let's see the first one. Okay, we learned about this one. Newton universal, the first one we learned. F equal G M1 M2 then bracket then over R square. Then number 2 we learn about the G gravitational acceleration. That's a G small g. Then after that Gm. This one M is normally for the Earth. Okay, for the Earth, then the R square. Okay, after that we learn about the centripetal force. Okay, when they just rotate. Okay, orbit. So we find it as a mv square over the r. Then you want to find the centripetal acceleration also can. That's a v square over r. Okay. Then after that, we continue to learn about the linear speed. Okay, for the satellite, for the any planet, v equal 2 pi r over t. Okay, after that, the mass of the Earth. This one is the last one we learned. Okay, when you want to find the mass of the Earth or mass of the Sun, you can using this formula. Okay, next one, we learn about Kepler, second law, third law, first law, is it? But we only got third law of formula. So the third law formula create from here. Okay, they create from here. So this 4 pi square over gm, this one is a constant value. Okay, there's a constant value. So finally, they create the equation. Compare two planet. Okay, two planet means T1, the first planet period square over the radius 1 cube equal the period for the second period square over the radius of the second planet cube. So this one is a third law equation. Or you can write T1 over T2 also can. R1 over R2, but both also is a cube, also can. Okay, so now today is a 3.3. So we go through what we need to learn for 3.3. Okay, we're talking about man-made satellite. Okay, normally they're talking about satellite mean you need to know the distance must be far a bit from the Earth. Okay, unless the question they tell you, now the satellite is on the surface. Then you can using the radius. Okay, if they're just far away from the Earth, that means you need to plus one more distance. Okay, so we go through. Okay, linear speed of the satellite. Okay, satellite, they move in orbit a specific height. Okay, they got certain height and also suitable linear speed. Okay, move specific height from the Earth. After that, they got speed for the satellite. So from here, okay, now we're going to see what we learn about the mass. Okay, capital M is stand for the mass of the Earth. Okay, small m sure is a satellite lah. And the satellite radius orbit satellite, that's a R. Okay, from the center to the satellite. Okay, suppose here is a bigger R plus H. Okay, after that we got linear speed. Linear speed, normally we want to count about the satellite to move, not the Earth to move. It's a satellite moving. So we need to count velocity for the satellite. And the last one is the orbit periods. So that means the satellite just one round, the time taken is how long? The one we call orbital periods. Okay, so we go and see. Okay, gravitational force between the satellite and the Earth, we learned before. Okay, centripetal, we also learned before. Both also pull to the center of the Earth. Okay, this one is pull center to the Earth, but this one normally we're talking about the pull to the center of the circular. Okay, you not only for the planet, we can say talking about the kids. When they just swing, that means the force pulling to the center. If we're talking about universal, that's a planet force pulling to the center of the Earth. So now I can put these two equations together. Okay, so finally we find it, they become G capital M. Okay, normally for the bigger object lah. Normally it's a planet. Okay, this one is normally for the satellite. Okay, so this one is a R. So when I just combine two. Okay, so from here, this one, when I just combine two together, satellite and satellite, the mass, suppose we can cancel. So the R, you can cancel 1. Because this one R square. When I just move cross already, then R can be cancelled 1. Finally, what I left it? So finally, I left V square GM over R. So just now I show you how to create the linear speed formula. So the linear speed formula like this. So this one linear speed, normally we're talking about satellite, because moving is a satellite, not the earth or not the sun to move it. Okay, so now you see this one as an example. Okay, we got one GPS satellite. Okay, they orbit around the earth. So from here, this one got H. They sure got H. They're not exactly at the surface, they are far away a bit. So from here, this one you need to know when you do the calculation for the radius. Okay, now radius of its orbit. Everybody must know you need to plus the H. Okay, there's a R, radius of the Earth. Small h is the distance from the surface to the satellite. So linear speed, how to do the calculation for linear speed? Okay, man-made satellite can be launched to keep orbiting at a specific height around the Earth at the radius of the R if the satellite is given linear speed. Okay, continue. So from here, if we want to find the linear speed, so the equation like this. Okay, this one is for the Earth. Okay, so why is for the Earth? You're going to see the formula. Mass for the Earth. So this one is radius for the Earth. This one is a distant satellite to the Earth. Okay, this one is a speed of the satellite. Okay, so this one is a constant value. G and M is a constant value. G is a constant gravitational, and the M is for the Earth. Okay, means the equation satellite speed round the Earth. So that means we never count this one is a satellite. If you count this one as the mass of the satellite, the meaning is you count satellite round satellite. OK， 所以这个大的 M 它是Earth，是代表 satellite 绕着这个地球的 distance 到底有多快。如果我们拿这个是 satellite 的话，的意思就是 satellite 去 round another satellite。OK， 所以这边的 M normally 我们没有写小的，我们写大的 capital M。OK， 我们才懂一个东西是固定的，那个就是你的太阳或者是你的地球。And after that， 绕着它走那个就是这个 V， 就是 satellite。你要找那个 satellite 到底走多快。So from here, normally they count about V. We need to talking is a satellite, how they go around some of the planet. Okay, so from here, 下面有解释给你看啊。So you can see, I think your notes got explained for you. You can refer your notes. They got page number 1. Okay, page number 1. They got mention about the formula for the linear speed. V square root gm over r plus h. Okay, linear speed V of the object does not depends on the mass of the object, but it depends. OK， 他讲的是 linear speed 没有关系到那个 satellite 的重量，因为那个大 M 是什么 mass of the Earth。所以只要你的 planet 重量换 ，OK， 我的 satellite 的 speed 就会换。OK， 你的 satellite 有多大多小没有关系。OK，so this one is a formula for the GM over R plus H。所以下面有解释给你听 ，mass for the Earth 是那个大 M。So distance of the object from the center 去到 Earth 就是 linear。They want the radius plus h. So 记得 when I want to find about the V square root gm, this one is for Earth. Okay, after that there's a r plus h. So radius. Okay, this one is height. Okay, this one satellite speed. Okay, so this one is a formula when you want to find the linear speed of the satellite. Okay, now you can see this question. Okay, 我们看这个题目啊。So this one is an example for your question. Okay, you can see you refer your paper. This one is the first question, example 1. So we see the info. Okay, they made a sub-satellite. Okay, they got one of the satellite around the Earth. Okay, after that they got distance, the height above the Earth's surface. Then the average radius of the Earth. Here, radius of the Earth provided, there's a R. And the mass of the Earth also provided, capital M. Okay, what is the linear speed? They want to find the V of the satellite in orbit. Okay, so from here, the info, Earth mass, Earth radius, G provided, then the H is kilometer, then we want to find the V. So from here, I can show the equation. You want to find the V. Okay, so now you press your calculator, you see what's the answer for the V. Okay, I'm going to check the answer from Xiaoling. Xiaoling, can you do calculation? Okay, remember when got H, better you do first because there's a plus. Okay, after you do, then you get the R first. Then you easier for your calculation. 7557. Okay, we're going to check. Okay, so this one is when you just put in. Okay, so if you want to put standard form, there's 7.56 lah. If you round number, 7557. Okay, so this one is a linear speed for the satellite to orbit the Earth. Okay, remember square root, then you get the answer. Okay, so this one is how we go and answer the question when you want to find about linear speed of the satellite. Okay, so this one is one formula about the satellite orbit the Earth. Okay, then we go to see the second one. Okay, we continue. Okay, just now is the linear speed. Now we continue with the another one. Okay, if the linear speed of the satellite become less, okay, less than the required linear speed. Okay, so the satellite will fall to the lower orbit and continue to revolve towards the Earth until enter the atmosphere. So that means this one is a satellite. They go to Langga, go in the atmosphere. Because the linear speed, you become less than the required speed. So what is the required linear speed? Later we need to see. So that means minimum, you sure got one of the speed. Okay, for the Earth, we got some linear speed. That means we need to control. So from here, if the satellite, you are lower, then after that, you will fall to the lower orbit. One orbit to lower orbit. Then you continue after that towards to the Earth until you go into the atmosphere. Okay, the movement of the satellite at the high linear speed against the air resistance will generate the heat and eventually causes satellite to burn. Okay, lower you fall to the atmosphere, but if higher, too high already also cannot. Too high, that means you need to overcome the air resistance. Okay, we not yet go to the space, still inside. So that means you still higher speed, you against the air resistance. You still got air resistance. After that, you will generate the heat and eventually causes the satellite to burn. So we still got air resistance. Okay, near to the Earth, we still got air resistance. So that means if you're too fast, you also cannot. You're too fast, that means you need to against the air resistance. Okay, when you just against resistance, they sure will produce a heat. Because of friction, you produce the heat. Finally, the satellite also can be burned. So this one is one of the linear speed you need to control. Okay, 太高也不行，它会跌到那个 atmosphere 的那个大气层。如果你太快也不行，它会创 air resistance 更快，产生它的 heat 更高，到最后它就会 burn. Okay, so this one is related with the linear speed of the satellite. Okay, now we go and see this one about the satellite. Okay, first one you see this one, satellite A. Okay, satellite A, they orbit this one orbit. Okay, so we call it as a geostationary satellite. Okay, when they orbit far a bit from the Earth. This one. Geostationary, later we see what's the differences. Okay, another one. They go near, there's a satellite B. Okay, nearer with the Earth. Okay, they call non-geostationary satellite. Okay, this one non, They can go in and go out. They're not exactly at the same orbit. Maybe they can go in near the Earth. They also can out further from the orbit for the satellite. It also can. Okay, now we're going to see what's the differences. These two satellites. Okay, both also orbit Earth lah. This one is a similar. Both also orbit the Earth. Then sure the other is differences. So we see what happened. Okay, we're going to see geosatellite first. Geosatellite means this one, this row. Okay, geosatellite in a special orbit, we name geosatellite orbit. So this one we call geosatellite orbit. The circle, the ellipse shape orbit the Earth, we call geosatellite orbits. Okay, now move around the Earth in same direction as the direction of the Earth rotate. So if your Earth rotate clockwise, they also follow rotate clockwise. So that means exactly same like the Earth to moving. So that means every direction also same. Okay, for the Earth to move. Okay, then after that we go to number 3. The note for number 3. Orbital period 24 hours. That's the same as the period of the rotation of the Earth. 它跟那个 Earth 一样，一天 rotate 24小时。Okay, exactly the satellite, exactly the rotation of the Earth. Always above geographical location. See, 它的意思就是跟那地球看，你看那个 map， 地球 map 是一模一样，它到哪里就是 satellite 到哪里。So that means they don't have any, or when you just until this part rotate, then the satellite move another side. 没有 exactly 跟它一模一样 location. Okay, so this one we call geostationary satellite. Okay, exactly same like the rotation of the Earth. Then the Earth rotate one round, 24 hours. They want the satellite also same. So that means everywhere from the Earth, they will capture exactly same like the Earth. So this one we call geostationary satellite. Okay, later we see where they go to apply. 我们在那里用这个 geostationary satellite. Okay, then we go and see non-geostationary satellite. What is that? Okay, non-geo 就是 either 这个 orbit 也可以 either outside orbit also can. So you see normally lower or higher orbit than the Earth orbit. 你要 lower than 这个 line also can. You want outside this line also can. So that means non-geostationary satellite, they're not a fixed line. They can move inside, they can move outside. Okay, orbit period. If you're inside, they're shorter law. If you're outside, you are longer law. So depends. So the satellite, there may be longer 24 hours, there may be shorter 24 hours. That means they not exactly follow the Earth to rotate. Okay, anyway, 它要走哪一边就走。Then one more, above different geographical location at different time. 它不一定跟那个 Earth orbit 的时间一样。当你转到这一 part， 可能我走去另外一边了，它没有跟它一模一样。So that means you rotate clockwise, maybe the satellite already is reverse clockwise. So this one we call geostationary satellite. 它不固定的地方走。Okay, orbit 肯定是绕着 Earth， 但是我可以转另外一边，你转右边，我转左边。OK， 当你转到这边是 Malaysia 的时候，照到太阳的时候，我的 satellite 可能跟你不一样，我可能在西边了，也是可以。So this one called non-geostationary satellite. Okay, never follow the rotation of the Earth. They may be lower, they may be higher than the orbit of the geostationary Earth. Then the 时间 longer, shorter also can. Then the geographical location, there also can be differences. Okay, so from here, we're going to see a specific more differences. Okay, what is the similarity? What's the differences? Okay, 一样的东西 formula 肯定一样。Okay, we're using the same formula to find the linear speed. Okay, although there's a geostationary satellite or you are non-geostationary satellite, we're still using the same formula because you still orbit the Earth. Okay, number 2. Okay, period. You want to find the period, also same. 4 pi square r cube. This one is for the Earth. Then you want to find the period, also same. Okay, maybe longer, maybe shorter. We don't know, but you're still using the same formula. Okay, and the last one, both also orbit Earth. Okay, this one is a 3 similarity for the geostationary and non-geostationary. Okay, now we see what is the differences. Okay, differences, we can see direction of the motion. Okay, where they go. For the geo, same as the direction of the Earth rotation. Okay, if the Earth rotate clockwise, then the geostationary follow. Okay, but the non-geostationary is not be the same as the direction of the Earth rotation. Okay, 它不一定要跟。Okay, periods. This one sure 24 hours. This one can shorter. This one can be longer. Okay, how about the positions? Above the same geographical location. So the line is always the same as the Earth to rotate. Okay, this one is above different geographical location. I mean 你转到这一边刚好向到太阳的刚好是Africa 那一 part then the satellite 不一定我可能在另外一 part 了 Okay, how about the satellite for the geostationary? That's exactly 你到那边是 Africa for the sun, then I also say. So that means that one is a position for the geostationary satellite. Exactly same like the sun. Exactly same like the Earth. Okay, another differences, function. Okay, function we use for geostationary is a communications. So on communication, you must follow exactly the Earth how to move. So the communication, you can get it. Now the time should be you are morning, then another side also is night. After that, when you just communicate, you can communicate at the same time. So now and at night, you are morning. So at the same time, I connect you, I also can be connected. So this is a communication satellite that's using by geostationary satellite. So that means they never slow. Okay, when I just talking, after that you need to wait until now you can get communication with me. No, that's exactly the same time. Okay, number 2, non-geostationary, they're using for GPS. So GPS not exactly follow the rotation for the Earth. They can go another side, they can go longer period, they can go shorter period. Another one is a weather forecast. Weather forecast can go anywhere to test about the forecast. They're not exactly round the Earth. They can go other way. Okay, example. Okay, normally they ask is an example. Okay, for the example for the geostationary, they're using as a Miasat. Okay, follow the rotation of the Earth. Okay, this one we got Tunsat, Pipit, Razatsat, and also the ISS. These all satellite they call non-geostationary satellite. They can move anywhere, but the orbit sure is the same lah. Okay, they can further, can closer. After that, they not exactly follow the geostationary location. Okay, this one is a 2 type of the satellite for the Earth. Okay, rotating the Earth. So normally this one just the concept when they ask you about the question. What's the function, example, then you give an example. Okay, so from here, we go to the last formula need to introduce for you. There's a escape velocity. So we got velocity, we got escape velocity. Escape velocity means now you want to go outside from the Earth already. You want to further some more. That means you already over the linear speed of the Earth. You want to go outside. So from here, you want to achieve minimum velocity required by the object on the Earth surface to overcome the gravitational force. You want to overcome the gravitational force, you must achieve the minimum velocity. After that, you can escape to the outer space. So that means for the planet, they sure got certain escape velocity. So different planet, different lah. So from here for the Earth, we sure got one certain escape velocity. So if the launching for the rocket, you want to go to outer space, so you need to create the speed for the rocket must over the escape velocity from the Earth. So after that, you no need follow the orbit of the Earth. After that, you can launch, go to outside. Okay, so now we need to find out what is the escape velocity of the Earth first. They sure is a constant value. Okay, then we also need to count what is your satellite escape velocity. Is it over the Earth or not over? If not over, you're still inside. Follow the orbit, then you move. If you're over, that means you go outside the space already. Okay, now we're going to see the formula for escape velocity. Okay, the escape velocity is achieved when the minimum kinetic energy supply to the object. Okay, object is normally is the satellite, the rocket lah. The rocket, or you see the satellite, is it over or not over? Okay, after that, they exit the gravitational potential energy. That means when you move, you got kinetic energy. Then after that, you want to go outside, they got one of the gravitational potential energy to pull you back. So you want to go, one another energy pull you to come back. If you over this one energy to pull you to come back, that means you can go outside. Okay, so from here exactly, you want to go outside. This one is your kinetic energy, mv squared. Okay, they got one of the energy pull you back to let you to go. There's a gravitational potential energy. Okay, EP. Okay, don't let you to go. If you over this one EP, that means you can go outside. It's straightforward, go outside. So means how to over the EP? You overcome the gravitation, the kinetic energy lah. Suppose this one is a half mv squared equal to the EP. Okay, if you cannot go up, there's an equal. If you over, then you more than the EP, that means you can go outside. So this one is energy conserve. Kinetic energy go outside. Gravitational potential energy don't let you to go. Suppose it's equal. If you want to over, then your kinetic energy must be big enough. That means you can go. How to make it big enough? Sure, it's a velocity lah. So the linear speed must be high enough. So this one high enough linear speed, we call what? We call escape velocity. Okay, if you over escape velocity, that means you already over the potential energy, then you can go outside. Okay, so the gravitational potential energy from here, the formula is a U equal negative Gmn over R. Okay, some you ask, okay, why got negative? Okay, the negative is, you can see the direction. When you want to go out, half mv squared, okay, direction is a positive lah, you want to go out. Okay, one of the energy, when you pull you to come back, this one we call it potential energy. So you can see the direction for the potential energy, there's an opposite direction with the kinetic energy. They want you to come back. So from here we put negative. Suppose the formula is a half mv squared equal plus energy, potential energy equals 0. Because both magnitude is the same. You pull, I pull you back, so equal to the 0. So how to more than 0? When your half mv squared more bigger than the EP, that means you can more than the 0, then you can go up. So when I just write the equation, suppose like this, negative EP. Okay, this one plus this one equal to the 0. And when I just put the equation, half mv squared equal EP. If it here is more than EP, that means you can go outside. So this one is a formula for the potential energy. But the question is seldom to ask you to find the potential energy. Okay, they just want you to find the escape velocity. Okay, so just let you to know we got one potential energy is don't let the rocket to go outside. Okay, if you still want to go, that means you must over this one potential energy. Okay, so we're going to see that exactly. Okay, you can see here. So this one, when the V, they want to go, half mv square. Okay, so we got one of the energy, there's a gravitational potential energy. There's a one you pull you to come back. Okay, pull you to back. So from here, we can write the equation half mv square equal to the negative Gmn over R. Okay, both energy is the same, just transfer only. So when they just equal, then they become zero lah. If you're over, then the half mv square become bigger than the gravitational, so you can go outside. So from here, gravitational potential energy, this object can overcome the gravitational force and move an infinity distance from the Earth. If you can overcome this one potential, that means you can go infinity already. So this one is one of the formula for the potential energy for the any object you want to go to space. So you must overcome the gravitational potential energy. So remember the negative is because opposite direction. They pull by opposite direction, so they put the negative for the gravitational potential energy. Okay, so R is stand for what? The radius of the Earth, of the object from the center of the Earth. Mass is small mass, is the object you want to go. Example, rocket. Okay, the rocket they want to launch to the space. Okay, bigger M sure is the mass. So from here we continue. Okay, they just one of the energy don't let you to go out. So if you just over this energy, that means no problem lah. You can go to the infinity already. So how to make it more important is this one, the V. Because half M, this one is the object, so suppose is a constant already. Only the V you can adjust. Okay, now you can see escape velocity. Escape velocity is achieved when the minimum kinetic energy of an object is able to overcome the gravitational potential energy. So minimum kinetic energy plus gravitational potential energy, there's an equal zero. So we show the formula, plus, minus, there's an equal to the zero. Get the opposite direction, so we put negative. So finally, the equation, suppose you can do like this, mv square equal, when I just put equal, then no more already lah, like this. Okay, if here I put negative, the reason is velocity like this, then gravitational like this. So one is negative, one is a positive. So I need to put the negative here. Finally, you are conserved because zero. If you more, that means this one no more zero lah. That means you can go to outer space. Okay, so from here, why I need to create the gravitational potential energy? Because I want to create escape velocity formula. Okay, now we're going to see this formula. This formula, I want to get V half mv square minus G R equals 0. Okay, I want to get V square. So from here, I just take the V square first, take out. Okay, so I need to show about the calculation. Okay, so from here, okay, better I move another side. Okay, we see this one first, this one. Okay, small m and small m I can cut. Okay, small m and small m I cut. Okay, so V I want alone. So G, 2 must be multiplied. 2gm over R. Okay, V equal square root 2gm over R. Okay, this one. So from here, when you want to go out to the space, we compare the kinetic energy and gravitational potential energy. Okay, so if the question asks you why this one is a negative, your answer is gravitational potential energy and kinetic energy, there's in opposite direction to come. Okay, so you want to overcome This one potential energy. So the answer should be not 0 lah. Then more than 0, that means you can go outside. Okay, so this one is one of the thing don't let you to go. 它好像一个阻挡力，不给你过这个 energy。只要你的 kinetic energy 一多过它，你就可以冲上去。Okay, so from here we need to find out the V you need how many, baru you can go outside. Okay, so from here this one is a formula for the escape velocity. Okay, what's the differences escape velocity and the normal velocity we learn? Okay, normal linear speed we just learn like this. Square root gm over r. The extra 1, 2. Okay, 只是多一个2罢了。Okay, like this. Escape velocity, the extra 1, 2 only. Okay, because from the kinetic energy, they get the 2, because half. So this one is the escape velocity formula. Okay, so from here, again, the same thing, escape velocity. Okay, we see what's the important notes. Escape velocity of an object does not depend on the mass of the object. So mean this one is Earth. Okay, they don't have any small m. No small m means they're not related with the object you want to go to outer space. There only is a m, mass of the Earth. When you're over the mass of the Earth, okay, you can go outside. Okay, but it depends to what? Okay, they depend the mass of the Earth. Okay, this one. And also the distant object from the center of the Earth. This one. Depend for the capital M and also the small r. Okay, so you can find what's the relationship. G is a constant, so we don't care about that. 2 also is a constant. So they're just related with the M and also the R. Okay, the Earth has larger mass. The escape velocity of the object from the Earth must be high value. Okay, I don't care about the mass. Maybe I say another planet. If the another planet, the mass is a higher, so understood, escape velocity should bigger. So that means you want to go out from the planet, that means you need bigger velocity. Okay, for our Earth is how many? Escape velocity is 11,200 ms-1. Okay, if you count by kilometer per hour, that's a 40,300. So that means you want to go to the space, you must over this one velocity. Okay, your baru can go up. Okay, so that means the question will ask you to count what is the escape velocity for the rocket. Then they will ask you, is it this one rocket can go outer space or not? And then you need to compare. Compare with the Earth and compare with the rocket escape velocity. Is it over or not? If over, that means they can go up. If not over, that means they're still inside the Earth. Okay, so from here, we're going to check the question how to come up for the escape velocity. Okay, today we learn about 2 formula only, linear speed for the satellite, and the escape velocity for the planet. Okay, only 2 formula for 3.3. So our lesson just until here, then we finish. Okay, only left about the tutorial question for yours. So we just end here. So see you on the next Friday again. Okay, everyone, bye and good night. Thank you.